Every second, the global economy executes millions of digital actions, from booking a flight to swiping a credit card. Under the hood, these actions rely on what computer scientists call a transaction. It's a single logical unit of work, bundling multiple dependent steps together. We expect these digital processes to run flawlessly, but the computers processing them are physical machines. They run on electricity, they have spinning drives, and they are entirely vulnerable to power outages, hardware malfunctions, and sudden crashes. Let's look at the classic textbook scenario, transferring money. We have account A starting with $1,000 and account B starting with $2,000. A user initiates a $50 transfer. The database executes the first step, deducting $50 from account A, leaving it at $950. But before it can execute the second step and deposit that money into account B, the power cuts out. The system crashes completely. That $50 is now in digital limbo. It's gone from account A, but it never arrived in account B. The database has been left in a broken, inconsistent state. When the server finally reboots, its main memory has been wiped clean by the blackout. The system has to figure out what happened in the milliseconds before it died. To prevent a scenario like evaporating money, computer scientists established a set of strict laws for databases, known as the ACID properties. The A stands for atomicity. A multi-step digital action must execute in its entirety or not at all. There is no partial transaction. The D is for durability. Once a transaction succeeds, its effects are permanent, surviving any hardware failure. If the hardware is dead and the memory is wiped, the machine can't enforce these rules in real time. It requires an entirely different mechanism to clean up the mess after the fact. The mechanism that handles this is the database's recovery system. The recovery system relies on a strict prime directive. Before the database is allowed to alter any actual data, it has to write down exactly what it plans to do and save that intention to crash-proof stable storage. This record is called the log. Every time a transaction starts, it creates a new entry, logging its own unique identifier and the specific piece of data it's about to change. Then it records the old value of the data prior to the modification and the new value it intends to write. By forcing the system to chronologically document the past state and the future state before doing any actual work, the database creates a perfect forensic blueprint. Let's go back to our crashed server. When power is restored, the recovery software doesn't immediately check the bank accounts. It goes straight to the log. Scanning through the ledger, it finds our interrupted $50 transfer. The log shows a start record, but no commit record. This triggers the undo procedure. The system reads the old value and rolls account A back to $1,000. It's as if the transaction never happened, achieving perfect atomicity. The system continues scanning and finds a separate, unrelated transaction. This one successfully logged a commit record right before the crash, but the blackout hit before those final changes could be safely written to the main disk. This triggers the redo procedure. The system takes the new value from that committed log entry and reapplies the change, guaranteeing durability. By tracing this log, undoing incomplete actions with the old values, and redoing committed actions with the new values, the software can trace its own steps to repair the damage. When the recovery is complete, the database opens for business in a perfectly consistent state. No money evaporated and no half-finished actions remain. The elegance of this solution is in the engineering mindset behind it. Instead of trying to build an impossible, unbreakable physical machine, database architects simply accepted that hardware will eventually fail. By enforcing this meticulous self-reporting with the log, they built software that can actively master its own timeline. This exact mechanism is running right now inside every bank, every airline, and every financial network on Earth. Our trust in digital permanence relies entirely on this invisible safety net, quietly imposing flawless order onto physical chaos.